Now I am going to start the master slave JK flip-flop. Before going to give you idea about the master slave JK flip-flop, the cause of introducing this master slave JK flip-flop is important. So I am revising the race around condition so that the problem of race around condition that we can remove by the application of this master slave JK flip-flop. Once again I am repeating this race around condition. Race around condition. So what is basically race around condition? The race around condition, so it is very clear, it will be clear from the truth table of JK flip-flop. So JK Qn plus 1. So when clock equals to 0, JK is in don't care condition. So we will get the output Qn as in the next state of Qn plus 1. And for when clock equals to 1, we will observe that the fourth state of JK 0 0 0 1 1 0 and 1 1. So when j equals to k equals to 0, we will get that Qn also in Qn plus 1, and 0 1 for Qn plus 1 is 0, and for 1 0 it is 1, and 1 1 it is Qn complement. So other three states we can that is the general steps. But whenever we will give the input j equals to k equals to 1, we will get qn complement is in output. So this qn complement basically creates one ambiguity, or as a situation that we can call the situation or condition that is called the racing. I am clearing more. It is the from the circuit of the JK flip flop by using NAND gates. I can use 4 NAND gates for explaining this. So here 4 AND gates are there. I can connect these AND gates. This is the feedback path. It is a J and K. Here clock is connected. Clock is connected, and here the outcome is Qn and Qn complement. Qn and Qn complement. So these three states, when j equals to k equals to 0, j equals to 0, k equals to 1, and j equals to 1, k equals to 0, is not so important for us, because this is a general output and we can get the stable output for each and every clock pulse. So for one clock pulse we will get a fixed state, but the condition is arised. One condition is arised when j equals to k equals to 1. So we will see that what is the basic problem that we will face when j equals to 1, k equals to 1. So as we can imagine that when Qn equals to 0, so Qn complement equals to 1 at initial condition, and j equals to 1, k equals to 1. And one feedback path should we should give a feedback path from this from this. Sorry. So this one is a feedback path is present from the Qn to K and Qn complement to J. One feedback path should be there. And when clock equals to 1, j equals to 1, and here Qn complement is 1. So that we can conclude that whenever the all input of any NAND gate is 1, the output should be 0. So G3, if I concentrate on the G3 NAND gate, so when all inputs are 1, then the output of this NAND gate is 0. And if one of the output of any NAND gate is 0, the output of this G1 should be 1. And this 1 is forwarded here, and here one of the input of this NAND gate is 0, so output is 1. So both of the output is 1, then both of the input of this G2 is 1, then output of G2 is 0. So if you can see that whenever Qn equals to 0 and Qn complement equals to 1, after giving one clock pulse, starting the circuit, after switching on the circuit, basically clock is 1. When clock is 1, now we will see that the circuit changed its output. At the time of switching on, the circuit changed its output to 0 to 1 to 1 to 0. And in the same clock pulse, after coming Qn equals to 1 and Qn complement equals to 0, this 0 forwarded to here, and when one of the input is 0, the output of this G3 is 1, and when all of the input is 1, the output of this NAND gate is 0, and after getting 0, this output of this NAND gate is 1 and output of this NAND gate is 0. So simultaneously, if I draw one clock pulse, so when clock is 0 and 1, so after switching on, we can observe the output. First initially Qn is 0, Qn 1, Qn 0, Qn 1, Qn 0, Qn 1, it is running. That is a 0 and 1, that is Qn. So in a single clock pulse, we can observe that the multiple change of Qn, we should get the multiple change in the Qn. Say here we have assumed initial condition Qn equals to 0 and Qn complement equals to 1. And as the condition we are deriving for j equals to 1, k equals to 1. J equals to 1, k equals to 1. And same condition that the clock should be 1. Because it's a level triggered, so when the clock fixed is clock is in the level 1, the circuit is on condition, other than circuit is in off condition. So we obtain the previous output whenever clock is 0. So that is the condition when j equals to 1, k equals to 1. So we observe that the change in the clock pulse is single. So single clock cycle, in a single clock cycle, the cycle is completed here, cycle is here. So single clock cycle in between this to this, that is a capital T. So when if we are concentrating on a single clock cycle, that is a half cycle, positive half cycle consisting of the positive half cycle and negative half cycle, that is a time period T. For a single half cycle, whenever clock equals to 1, we should observe some changes in the Qn, and when clock equals to 0, we can't observe any change in the Qn. So whenever the clock is equals to 1, that means clock is in high condition, we will see that multiple change in the Qn. So first when Qn is 0, Qn plus 1 is Qn complement is 1. After in the same cycle, next is a 1 0. We should observe 0 1 1 0. This continuous changing of the output, it is observed when clock equals to 1, and this continuous changing is called the racing. This continuous change is called the racing. Now I am talking about the racing, how to remove the racing condition. So this racing is such a condition that creates a confusion or creates some problem to the developer or circuit designer. Basically, this racing condition, we can't conclude that a fixed output in the racing condition. So when j equals to 1, k equals to 1 and clock equals to 1, we can observe a multiple change in the Qn and Qn complement. So if I place two LEDs in the Qn and Qn complement, we can see that the LEDs are glowing and off continuously, on off we will observe in the Qn and Qn complement. So this is a basic problem facing by the circuit designer or the programmer, or you can say that the user. So to remove this situation, the situation only ambiguous situation creates when j equals to 1, k equals to 1 and clock is also 1. So this racing, we should remove the racing condition. So racing condition can be removed by two ways. How can we remove this condition of first say that we can say that the first way to remove this racing condition, if we can give a name of this as a TP pulse time, and can say that there is a pulse duration PD, can give the name of PD, pulse duration, or you can give I can give it as a pulse duration, positive half cycle or negative half cycle 0 and 1 0, or you can say that the single so pulse duration is a single pulse whenever the qn is 1 or qn is 0, that is a pulse duration. So if I can make the first way I can apply the to remove that the two ways to remove this race around condition, to remove this race around condition, we can apply two ways. First one, if I can adjust PD greater than TP, that means if we can manage this TP should be smaller than this PD. So if we can arrange this TP should be smaller than PD, so that at one clock cycle we can observe a single change in the output. So this if we can manage this the propagation delay, that is a PD, propagation delay and pulse time, delay and pulse time. So if we can manage the pulse time should be lesser than the PD, then we can remove this race around condition. Is the first way to remove this race around condition. But the thing is that PD is very small range, is in the nanosecond range. So in practically the TP in nanosecond range or lesser than this nanosecond less, creating pulse time TP in nanosecond range is very difficult. Very difficult. So practically it is not used. Not used. So the second method is left. A second way is left to remove this race around condition. So second way is the use of master slave JK flip flop. Master slave JK, that is operated in age triggering. Principle. Age triggering principle. So first one is that in this case we can consider the level triggering, but in case of master slave we should consider the edge triggering. So now we have got that why should we study the master slave flip flop. So now we can start the master slave flip and start to understand the master slave flip flop, because we want to remove the race around condition that is arised in the JK flip flop when J equals to 1, K equals to 1 and clock equals to 1. That is the race around condition. So now can start the master slave flip flop. Now master slave flip flop basically is an arrangement of two JK flip flop. I can write the block diagram of master slave flip flop. So this one is a one JK flip flop, this one is another JK flip flop, and we need to connect this both flip flop as like this: JK, JK, QM, QM complement, and that is a QN, QN complement, and that is a JK flip flop, JK flip flop, and one feedback path is connected from here to, because this is a JK flip flop concept, we have to connect one feedback path here. Now this one is a master slave JK flip flop, and one thing is left, that is a clock. We should give the clock, that is the master slave arrangement of JK flip flop. One NOT gate is present in between clock pulse of two flip flop. It will be better understandable if I can draw this by using the NAND gates. So if I can draw this both JK flip flop by using NAND gate, it will be more clear to you. So I can draw this circuit of master slave JK flip flop. So for this I have to take 8 NAND gates, 4 NAND gates for master, 4 NAND gates for slave, and these 4 NAND gates I have drawn for the master, and next 4 NAND gate I am drawing for the slave. And it is a very interesting thing, that is the concept of master and slave. Basically slave always follows the master, so that we have given the name of one of the flip flop is a master, another flip flop is a slave. That I am connecting this flip flop. Here is a clock connected, and this flip flop is connected, this flip flop is connected, one feedback path is present here. This is a QM, this is a QM complement, this is the QN, QN complement. I have to connect here the clock. Here is a J, here is a K, and one another thing is a feedback path from the input to output to input, and this feedback path is connected here. Now we have we have completed the circuit, and this clock is connected with the second flip flop by using one NOT gate. So now this circuit is completed. I am giving the name of the NAND gates: G1, G2, G3, G4, G5, G6, G7, G8. Yes. Okay. So condition is the same. When I am discussing the race around condition, master slave is a is used for removing the race around condition, so that I am considering j equals to 1 and k equals to 1 condition. So when j equals to 1 and k equals to 1 and also clock equals to 1. So clock equals to 1, that means here two flip-flop are there. This one is one flip-flop. This one is another flip-flop. This flip-flop is called master. This flip-flop is slave. So why it is called master? Because in the clock cycle, whenever we are providing the clock, so for the positive half cycle or positive age, for the positive age, this flip-flop is in on condition because it is in 1, clock is in 1. So whenever clock is in 1, 0 to 1, flip-flop is activated or this flip-flop is 1. So when this flip-flop is 1, we can get the output from QM and QM complement. We can get the output from Qn and Qn complement. But at that time, if it is a 1, so flip-flop of this flip-flop is on condition. But when it is a 1, so here we can get the 0 because it does not get present. So 0 deactivates this flip-flop. So this flip-flop is in off condition. So we can't observe any output from this end. After that, whenever this flip-flop is from 0 to 1 to 0 condition, 1 to 0 condition. So in 1 to 0 condition, this flip-flop is in off condition, off situation. So this 1 becomes to 0 and this 1 becomes to 0. So this 1 becomes to 0. So this 0 becomes 1. So this flip-flop now in on condition. So when this flip-flop is on condition, so this flip-flop is active. Now this input is in QM is and QM complement is considered as the input of this G3 and G4. Now we can observe the QN and QN complement. QN and QN complement from this QN by using QM and QM complement. We can see this from the diagram of clock pulse. It will be more clear. 0, 1 clock. So when QM, we can see the QM. So QM is in on condition. QM, we can get the output of QM from 0 to 1. So when the first clock pulse from 0 to 1, clock pulse is from 0 to 1, we can get the QM is 1. After completion of the half cycle, this flip-flop is in off condition. Now this QM is not changed. So when this QM is changed once again, when we can get this flip-flop clock input from 0 to 1 again. Again from 0 to 1, if we observe the clock from 1 to 0 and next again 0 to 1, then this flip-flop once again is in on condition. Then we can observe a change in QM. QM is changed. So QM is changed in the next positive half cycle, positive edge of the clock cycle. So by this way we can observe the changes in the QM 0 and 1. When this flip-flop is in on condition, this flip-flop is in off condition. After half cycle, whenever the clock is from 1 to 0, that is in negative age, this flip-flop is in on condition. So QM is considered as the input of JK. So whenever this negative age is coming, the QM reflects the QM. At the negative edges, it changes its state at the negative edges of the clock pulse. It shows its change in the negative edge of the clock pulse. So why it is called the master slave? See this. So slave is depend on the input of the master, output of the master. So here is the output of the master is a QM and QM complement. So when clock is equals to 1, can observe the QM and QM changing in QM when clock is equals to 0 to 1. Clock is changed from 0 to 1, that is a positive age of the clock pulse. So we can observe the change in the QM when first positive age of the clock pulse. We can observe the change in QM. But this QM change, next QM change, we can observe this next QM change when next positive edge is arised in the clock pulse. So it is a fixed being between two positive edge of the clock pulse. So it is not changing its state. So output is not changing its state within one clock cycle. So in one clock cycle, we can get a fixed output from this master slave. So if we first after that QM is fixed and this QN is depend on this QM. So here it is called, this flip flop is called slave because slave output is taking the input of the master. So master's output is considered for the slave input, so that this slave is always depends on the master. So that this arrangement is called master slave arrangement or master slave JK flip flop. So in this master slave JK flip flop, only one change is observed in a single clock pulse. In a single clock pulse, we can observe a single change, only one change in a single clock pulse. And this concept is called toggle. This concept is called toggle. So toggle is a toggle whenever the j equals to 1, k equals to 1 and clock equals to 1. At that time, if we can use the master slave flip flop, that master slave JK flip flop. So master slave JK flip flop fixed in a, the output of master slave JK flip flop is fixed in a state that may be 0 1, that may be 1 0. So this fixed stayed in a fixed state, that property is called toggle. Toggle or toggling. So this is a very vital use of master slave JK flip flop for creating toggle condition, or for application of building the toggle circuit. Toggle circuit, master slave flip flop is widely used. Based on this concept, the next flip flop is derived, that is T flip flop. That is a concept of T flip flop or toggle flip flop. T flip flop or toggle when the j and k equals to 1 or k j equals to 0. Basically, when j equals to k. Based on this concept, the next flip flop, that is a T flip flop, is built based on the j equals to k concept. So when I can draw the block diagram of this toggle T flip flop, that is JK from the JK flip flop concept of JK flip flop, that is a clock pulse. So can connect the j and k, shorted the j and k, and qn complement. QN complement this is the JK. JK is connected, JK flip flop. So here clock is connected and J and K is shorted, and it is a T. Input is T. So that truth table can be derived from the concept of the JK flip flop. I can write the truth table of JK. So truth table of JK clock. Once again, I am writing the truth table of JK flip flop. Qn plus 1, 0, don't care, that is a Qn, 0 0, it is Qn, it is 1 0 1, it is 0, it is 1 0, it is 1, and 1 1, it is Qn complement. So from this table we can say that the T flip-flop, for the case of T flip-flop, the J equals to K equals to 1 condition we should consider for this. So can reduce the table and clock T and Qn plus 1, that is a truth table. 0 don't care Qn, for 1 it is 0, for 1 it is 1. So when it is 0 it is Qn, and when it is 1 it is Qn complement. Qn complement. Qn and Qn complement. So can draw the block diagram of T flip flop. Is a age trigger. So I can show the symbol of clock. There is a T, that is Q and Qn complement, and T flip flop. That is a block diagram of T flip flop. From this block diagram, I can from this truth table, I can write the characteristic table of this T flip flop. So present state, that is Qn and Qn complement, Qn and characteristic table. So here Qn T, Qn plus 1, that is a MSB is a Qn, LSB is a T, 0 0 0 1 1 0 1 1. So when T equals to 0, Qn should be 0. T equals to 1, Qn should be Qn should be Qn. So Qn equals to 0, so it is 0. So T equals to 1 when the Qn plus 1 is Qn complement. So Qn complement, that means it is 1. So when T equals to 0 it is Qn, and T equals to 1 it is Qn complement. So 0 1 1 0. And from this table we can write the directly we can write this as the 4-point K-map for Qn plus 1. So 4-point K-map of Qn plus 1, that is 0 1 0 1, that is Qn, and MSB LSB, so 0 1 1 0. So for this is the Qn plus 1 equals to T Qn complement plus T complement Qn, or Qn complement T complement Qn. So that is the characteristic equation of this T flip-flop. And again the excitation table is left. Excitation table of T flip-flop. So excitation table is a Qn present state, Qn plus 1 next state, and T. Here it is input, it is output. So when it is considered as input, is output input. So output and input. So when the output combination 0 0 0 1 1 0 1 1 output combination, so that as depend on the Qn, that is a 0 1 1 0. That is the excitation table. From this excitation table also we can draw the we can get the Boolean expression of T also. Boolean expression of T is like this: T equals to Qn complement, Qn plus 1 complement, and Qn complement Qn plus 1. So that is the T from this table excitation table. That is up to the last type, that is a T flip-flop, toggle flip-flop. T flip-flop is a one case of specific case of JK flip-flop when J equals to K. That is a T flip-flop.